Hi everybody, welcome back to Transcended Institute. So in this video we're just going to answer a chemical kinetics worksheet for 2025. It's been a minute, we've had a video on YouTube, so let's get into it. Okay, so these are the questions we're going to answer. What are the factors that determine an effective collision? For a certain reaction, the values of the Arrhenius factor and activation energy are given. Determine the rate constant. So all the questions all the way up to 9. At least they test the different aspects and concepts of this cardinal topic in chemistry. So we'll break it down for you. Let's get started. Okay, so I'd advise you, if you've come across this topic already, pause the video, try out the question before I answer it, and compare your solutions. Okay, question 1. What are the factors that determine an effective collision? Okay, so if you are part of the people that have watched my topic on chemical kinetics, you would understand that in terms of defining chemical kinetics, we define chemical kinetics to be the study of the rates of reactions. Okay, now not only the rates of reactions, but also the reaction mechanisms. That's what we study under chemical kinetics. Okay, now within the reaction mechanisms, you would understand that when we are talking about the factors that affect the rate of the reaction, okay, there are actually two important things that we take note of. One, which is the collision theory, where this question is coming from. Now, under the collision theory, it actually states that for a reaction to proceed, the idea is that for a reaction to proceed or for a reaction to happen, particles of the reactant must do what? These particles of the reactants, let's say the reaction between A and B, their particles must collide. Okay? Now, not all collisions are effective. So for it to be effective, they must be, number one, the particles must possess sufficient energy. There is a minimum amount of energy required for a reaction to progress, which we call the activation energy, symbolized by capital E, small letter A. So that's number one. Number two, would you give it a guess? The other factor that is required for an effective collision is the correct orientation. Okay, so orientation is also important. So I think the suitable words to use would be proper orientation, the way the particles are oriented as they get to collide. These two factors are very important for an effective collision. Yeah, so that's what the question 1 was actually dealing with. Okay, now move to question 2. Now question 2, this is actually not very common, where the question proceeds directly to the Arrhenius equation. Okay, so the Arrhenius equation is as simple as K is equal to E, so let me use a different color, E to the power negative EA over RT. Now there is an A. Okay, so now what do these stand for? This stands for the rate constant, A stands for the Arrhenius factor, and then the EA stands for the activation energy. The R stands for no, R stands for the rate constant. I think I need to make that distinguishment there. So the R is what stands for the rate constant, and then the T stands for the temperature. Okay, yeah, I think that's very important there. Sorry for that. Okay, so now this equation can actually be broken down if we introduce a natural log on both sides. The equation would appear something like natural log of K, and then you know that when you are multiplying 2, so when you say natural log of AE, it can be broken down as what? It can be broken down as natural log of A, and then of course plus the natural log is actually the reciprocal of, it's the inverse of the exponential function. So we will just basically end up with negative EA over RT as the equation in the other form. Okay, so now how do we handle it in this case? If we look at the piece of information given in our equation, so we have K is equal to A and then exponential negative EA over RT. So the issue of the K and the R confusing us is very common. So the K, I think it better qualifies to be the reactions rate constant, and then the R is kind of like the gas, okay, rate constant, which is given as a constant in your exams, and then this one is one that's dependent on the reaction that you're talking about, and that's what we're trying to find in this case. Okay, so let's just substitute what we are given. I'm talking a lot. So K is equal to our A in this case is 4 by 10 to the power 3 to the power 15. So that's the collision per second. So that's the Inus factor. And then exponential is just a function on your calculator. And then our activation energy is the second part, which is 90. So if there's a negative in the formula, so negative 98.6. Now that kilojoules that you are seeing, we can actually expand it so that we don't have the kilo. Okay, so by expanding, the 98.6 is supposed to be multiplied by 10 to the power 3, which of course would give us 98,600 joules. That's joules per mole, and then divided by the gas rate constant. Each time you're dealing with chemical kinetics, just know that it's 8.3145. Okay, and then that's multiply by the temperature. The temperature should be in Kelvin, which has been given to us in Kelvin already, 303. Okay, so now do well to grab your calculator and just perform the calculations there. Okay, so what do we have? So negative 98,600 divided by 8.3145 divided by 3, so I'm doing that, divided by 8.3145 and then divided by 303. Okay, multiply. So now you punch your exponential in the calculator, raise to the result that you're getting there, and then multiply by 4 times 10 to the power 13. Okay, so the answer I'm getting in my calculation is something like, in exponential form, is 4.02 times 10 to the power negative 4. Okay, this is second negative. Okay, you can look at the units that we've been working with. You'd understand that from the collision per second there, that's where our unit is coming from. Okay, so second negative, this is our answer for question 2. Question 3. Question 3 is testing us on the rate of appearance and disappearance for the different parts of the equation. So what we have is A plus 2B, and then this gives us 3C, and then plus 2D. Okay, what are we given? What are we given here? We're given that the rate of disappearing of B is 1 times 10 to the power negative 2 molar per second. Where is our B? Our B is right there. So let's come up with an equation that relates the rates of appearance and disappearances for all these in the question. So by default, okay, by default the reactants are disappearing in a reaction and then the products are forming. So the formation is what we're calling the rate of appearance. So under chemical kinetics, when we are writing the rate, it can be expressed in terms of both the reactants and the products. Okay, we use the stoichiometric coefficients. So check out the way it's going to come out. So it will be negative change in concentration of A over the change in time, plus, so not plus necessarily, that's equivalent to the negative 1 over 2 change in the concentration of B over the change in time, and then would continue 1 over 3 change in C over the change in time, and then which is equal to the 1 over 2 change in concentration of D over the change in time. So just to give you a simple basic explanation, the reason why we're adding negatives for the reactants is because that's the rate of disappearance. So we'll put square brackets to indicate concentration. Okay. So the reason why the first one doesn't have any number is because we have a 1 over 1 is as good as not putting it there. So this is what we're going to use for our answering there. Now what we're given is the rate of disappearing of B, so this part is going to be useful. And then we are taught to first of all find the rate of disappearance of A. So which part of the equation is relating A and B? Just the first two. So negative change in concentration of A over the change in time is equal to negative 1 over 2 change in concentration of B over change in time. So the rate of disappearance of B has been given. So the rate of disappearance, in simple terms to you, it should appear as a negative in our equation. So the way this one is appearing, this is the rate of disappearance of A in its original appearance. Okay. Now I'll do something crazy here. I'll pull out the negative, and then I'll say negative change in concentration of B over change in time, and then I'll pull out the 1 over 2 there. So this part which is having the negative represents the rate of disappearance of B. Okay, whenever you see the rate of disappearance of B, just put the change in concentration over the change in time and add the negative there. So therefore the rate of disappearance of A is going to be equal to this part. The rate of disappearance has already been given as 1 times 10 to the power negative 2 molar per second. Now we are multiplying by 1 over 2 at the end there. Okay, I think this is very, very key and very important for us to understand. And yeah, what do we now get as our answer? So our answer is 5.0 times 10 to the power negative 3, which is also molar per second. Okay, I hope you get that. I hope you get that. So I need to indicate the answer there to say the answer is 5.0 times 10 to the power negative 3 molar per second. Now B, which I expect you to pause the video and try it out with a good explanation that I've given you. Pause the video and try out B. So we'll start with the rate of appearance of C. Okay, so at this point we've got options. What are the options? We now have the rate of disappearance of A, and then we also have the rate of disappearance of B. Now we can get any of the two that we want. What we want to find now is the rate of appearance of C. So C. So I'll go just for A now. Negative change in concentration of A over change in concentration, change in time, sorry, should be equivalent to 1 over 3, and then the change in concentration of C over the change in time. So what are we trying to find? We're trying to find the rate of appearance of C. Now this in its existence, negative of that represents the rate of disappearance of A. So which is just 5 times 10 to the power negative 3 molar per second, of course, which is equal to 1 over 3. Now this part, since it's positive, it represents the rate of appearance of C. So we can do away with the 3 that is appearing there, by multiplying by 3 throughout, so that we do away with 1 over 3. Okay, so that will divide, so that we just ultimately remain with the rate of appearance of C. Now when you multiply the two there, what are you going to get? So 3 times 5 is 1.5, oh sorry, 15. So 15 times 10 to the power negative 3 molar per second is equal to the change in concentration of C over the change in time, which is the rate of appearance. Now this doesn't make sense to a scientist, so even your calculator won't give you 15 times 10 to the power actually negative 3. It's as good as writing 1.5 times 10 to the power negative 2 molar per second. Okay, so that's our answer for C. Now I want you to pause the video. Pause the video. I've removed the formulas to see if you're able to remember. I want you to find the answer for D. Okay, I want to see the comments in the comment below the answer to question 3B. Okay, that I've not answered. Okay, so just in case you've paused the video and you've attempted to answer that one, where you've got 3 options to use the answer for A, B, and C to help you find D. You can use any of them. Okay, so the answer that you should get should be, okay, I won't give you, give me a comment and I'll actually check your answer. Who knows what you may win yourself. Question 4. A reaction has a rate constant of 0.0, okay, 0.051 minutes negative, which of course already indicates that's a first order reaction. If we begin with a 0.10 molar concentration of the reactant, what is the order of this reaction? So that's question 4. What is the order of this reaction? I already actually gave you the answer even before reading it. So this is first order. Okay, so if you are a person who doesn't understand how I've said it's first order, I've explained chemical kinetics as a full topic on our site. The link is in the description below. In fact, you can learn the entire chemistry course from stoichiometry all the way up to organic chemistry with tutorial sheets, worksheets, quizzes, and the videos explaining all the concepts readily available with the past papers. Okay, so how do you tell it's a first order? Okay, by looking at the units of K. Okay, so the formula that we usually use is, you look at this, what do we look at? So units that exist in a constant are m and a second. Okay, so you find that the formula is as simple as, for us to get first order there, if you substitute the overall order of the reaction, is it something like 1 minus n, and then second, this one is just permanently negative. So to find the units for K, just substitute. N is the overall order of the reaction. So the second negative represents time. It may be seconds, it may be minutes. Let me just put T negative. So in this case, if you try for first order, okay, let's start with 0. If you put 0, if n is equal to 0, the units are going to be molar per second. If n is equal to 1, it will subtract, m will disappear, so it will just be time negative, which of course would be second negative or minute negative. And then if you try the second order, it's going to be m, if you put a 2 there, it's going to be negative 1, and then time negative 1. So it's the first order that matches up. What is the concentration? What concentration of the reactant will be left after 3 hours? Okay, so if you want to be smart, don't even waste your time. The rate constant K has been given in minutes. Just convert the 3 hours to minutes. We have 60 minutes in an hour, so that would be equivalent to 180 minutes. So that's our time. Now what's the equation that we use when you're dealing with first order? The integrated lateral for the first order is natural log of final concentration. So I've given you ways and means to remember all these on our site. The link is in the description below. You can easily remember for the 0, the first, and the second, and also how to find the half-life. Very detailed. Okay, So natural log of the initial concentration. So how do we find the concentration? So the concentration that we are finding after 3 hours, do you think it's a final or the initial? So after, so that's the final. So this is what we're trying to find. Now what was the initial? The initial is given to be 0.10. Okay, so natural log of our final concentration, our K, which is there, is 0.0051. Our time is 180 minutes. Okay, so 180 minutes. So minute negative is as good as over a minute, and then 180 minutes, which will just cancel out at the end of the day. Okay, so plus the natural log of the initial concentration, which is 0.10. Okay, good, good. So natural log of our final concentration is equal to, so let me grab my calculator there. So negative 0.0051 multiplied by 180 plus the natural log of 0.10. Okay, so the value that I'm getting there is negative 3.220585. Now at this point you're good mathematics students, so you understand that natural log is the same as log of E. It's just a smart way of writing that. So you understand you can move that it goes the other side, it becomes the base for this part. Okay, so what we have is, we remain with a natural log of final concentration is equal to E negative 3.220585. Okay, so locate the E on your calculator and then add negative 3.220585. So the answer you'd get is 0.4, no, it can be bigger, it should be smaller, 0.040 molar concentration, which actually indicates that, okay, as the reaction proceeded, the concentration was reducing. Okay, now C says calculate the half-life. The simple formula for the half-life is just the natural log of 2 for the first order reaction. So natural log of 2 over K, this is the half-life for the first order. Okay, so you can just substitute natural log of 2 on a calculator, and then the constant was given to be 0.051 minute negative. So which entails now the half-life is just going to become minutes, right? So that would be 135.91 minutes. What's the half-life, by the way? So the time it takes for the concentration to cut into half. Okay, a reaction of second order with respect to a reactant. Let's read that question again. A reaction of second order with respect to a reactant. How will the rate of reaction be affected if the concentration of this reactant is doubled? I'll read that again. A reaction of second order with respect. So let's write the literal. So the rate is equal to K to a reactant. So assuming that's a single reactant. A reaction of second order with respect to a reactant. So let's call our reactant A. So it can, if it's only a single reactant, it can be second order if it's the power 2. Okay, if you're new to literals, don't worry, don't trouble yourself. Register on our site and you'll be able to understand what literals are. It's just an equation that relates the rate of a chemical reaction to the constant and the concentration. Okay, how will the rate of the reaction be affected if the concentration of this reactant is doubled? Okay, so that's the first one. Observe this. Now the question is, how will the rate of the reaction be affected if the concentration of this reactant is doubled? So what happens when we double the the concentration. So that would be 2a and then squared, right? So our H2, so this is going to be, if you square that, what are you likely to have? So you're going to have k multiplied by 4 multiplied by a squared. Now the first one is just k a squared, right? So if you compare them, okay, so the second one is like 4 times the first one, right? If you plot the constant. So in other terms, as a smart student, you know this part is equal to R1, right? So you can just write it as 4, and then we have is k a squared. That's where you put the R1, right? So you see that this, how will the rate of reaction be affected? So the rate of reaction will be 4 times. Okay. So the rate of reaction will increase by the factor of 4 when we double the concentration. Okay. So that's it to this video. If you want to access the full solutions, please use the link in the description below and register on our site to support our team. Okay, I hope you enjoyed and I hope you've learned something under chemical kinetics. See you in the next one.